Hello everyone, this is Kirtika Arya from IIT Roorkee. I am here to give a presentation on the topic second order response system with the different value of a damping factor. Now let's see introduction. The step response of a second order control system with different values of a damping factor provides insight into how the system behaves in the terms of overshoot and settling time. The damping factor determines whether the system response is underdamped, critical damped, and overdamped. And in other words, we can say that the time response of a second order control system is to tell us how the system behaves when it is subjected to a various input signal. These are the four parameter. Uh, these are the from four parameter we get which we get from the signals. First one is the rise time. Rise time is a time which takes for the system response to go from a lower value to a higher value by following a step input. Second one is the settling time. Settling time is the time which takes for the system response to stay within a specified tolerance band around the final steady state value. Third one is a peak time. Peak time is the time at which the system response reaches its maximum value before settling. And the fourth one is a maximum overshoot. The maximum overshoot percentage by which the system response exceed the final steady state value before settling is the maximum overshoot. Now let's see what is the time response of a second order system in control system. This is the block diagram of closed loop control system. This is the open loop transfer function which is connected to a negative feedback. This is the unit. Open loop transfer function is connected to the unit negative feedback. RS is a Laplace transform of input signal and CS is a Laplace transform of output signal. Now we know that the transfer function of the closed loop control system having unity negative feedback is Cs upon Rs equals to Gs upon 1 plus Gs. Now we substitute Gs equals to omega n square divided by S into S plus 2 zeta omega n in this equation, from which we can get the transfer function. Cs upon Rs equals to omega n square by S square plus 2 zeta omega n S plus omega n square, where omega n is a natural frequency and zeta is a damping ratio. Because the power of S is 2 in the denominator term, then the transfer function is the order of second, and the system is called the second order system. This is the characteristic equation of a transfer function from which we can get the roots of S. By the roots of S we can define the systems. If the two roots are real but not equal and zeta is greater than 1, then this system is called overdamped system. And these are the roots which are not equal and lies on real axis, is then the system is called overdamped system. For MATLAB code, this is the first part of MATLAB code from which we get graph of overdamped system. First we define the natural frequency omega n, then we define zeta 1.6. Zeta we get 1.6 because zeta should be greater than 1, that's why we write 1.6. For the uh, transfer function is equals to omega n square divided by S square plus 2 zeta omega n S plus omega n square. For now we write the formula of transfer function. For numerator we write omega n, and for denominator we write a Row matrix we define is as a row matrix with the coefficient of 1 and 2. Then this is the t this is the t equals to this is the limits of graph. This is the starting point, this is the steps, and this is the ending point. Then g equals g is the transfer function. Step this is for graph, and this is the labels for the graph. And now this is the second part of the system. Now this is the second part of the system from which we get the damped frequency. This is the formula of damped frequency. This is the formula of theta. This is for rise time, this is for peak time, this is for maximum overshoot, and this is the settling time. This is the now this is the output of our MATLAB code. Omega in natural frequency is 10, and we get the transfer function is like this: 10 divided by s square plus 32s plus 10. And this is the step response of second order system is under that system. This is the output of the parameters. This is the rise time, this is the peak time, this is the maximum overshoot, and this is the settling time. Now if the roots are 2 and imaginary, and zeta is equals to 0, then the system is called undamped system. For the roots is lie on the imaginary axis. This is the MATLAB code. MATLAB code is same to the previous one, but um, only changes that zeta is write as 0. We write zeta equals to 0 here, and it is same as previous one. This is the second part of the system from which we get the damped frequency, theta, rise time, peak time, maximum overshoot, and settling time. This is the output of the system. This one is the graph of undamped system. Undamped system. This is the transfer function of undamped. G equals to 10 divided by s square plus 100. This is the rise time of the system, this is the peak time of the system, this is the maximum overshoot, this is the settling time of a system. For underdamped, if the two roots are complex and conjugate, and zeta is lie between 0 to 1, then the system is called underdamped system. For underdamped system, these are the roots. For underdamped system, MATLAB code is same. The changes we write zeta equals to 0.6 because zeta should be lie 0 to 1. This is the first part of a same as previous one. This is the second part of the code from which we can get the parameters of signals. This is the transfer function of underdamped system. G equals to 10 by s square plus 12s plus 100. This is the graph of underdamped system. This is the rise time, peak time, maximum overshoot, settling time. For now, let's talk about the critically damped. If the two roots are real and equal, means both are lies on real axis and overlapping, then the system is called critically damped system. Uh, their zeta should be equals to 1. there is a change in code is only zeta equals to 1. Then the system is called the critically damped system. This is the graph of the critical damped system. This is for the MATLAB calculation. This is for the part, calculation code part. This is the second part of the system, from which we can get rise time, theta, peak time, maximum overshoot, and another. This is the output of critically damped system. This is the graph which we get. This is the transfer function g equals to 10 by s square 20s plus 100. This is the rise time infinity. This is the peak time, which is infinity. This is the maximum overshoot, z, which is 0. This is the settling time of the system, which is 0.4. And thank you so much for listening my ppt. Thank you so much.